Hello, dear students. Assalamu alaikum. Today I'm going to solve a question related to Cambridge A2 Physics syllabus, nuclear physics. Name of the chapter is nuclear physics. So before solving the question, let me tell you something about Cambridge A2 level physics syllabus. Cambridge A2 level physics syllabus is very difficult in comparison to Cambridge AS level physics. In Cambridge A2 level physics, you need to sit for two papers, paper 4 and paper 5. Now, paper 4 is going to carry 100 marks and 2 hours exam, so that will be very difficult. And also, the syllabus of the Cambridge A2 is quite bigger and harder than Cambridge AS physics. Just let me tell you some of the name of the chapters of Cambridge A2 physics. So, total you need to study total 13 chapters, and in 2022 May June session, you have to you will sit for a new syllabus, new specification. You can download it. So download the specification immediately and check the syllabus properly. And also a new syllabus book is available. Collect it immediately. So look at the content of A2 syllabus here. Total 13 chapters. And if you look at the name and content of each chapter, you can understand that it's not going to be comparatively easier than AS. Definitely it's going to be difficult, like gravitational field, temperature, oscillation, capacitance, magnetic field, alternating current, quantum physics, nuclear physics. All chapters are comparatively harder than whatever you have studied in AS level physics. So that's why you need to go through these chapters very properly. Moreover, the paper 4 exam is 2 hour, 100 marks. So paper 4 will play a crucial role in overall result of your AS and A2 altogether. So you have to be very careful while studying A2 physics. Okay. And you need to go through the chapters elaborately, and at least you need to solve minimum last 10 years question. Try to solve all the question like May June session question, October November session, and February March session as early as possible. Okay. And you can download all the questions. There are lot of sites. Just search Cambridge A2 physics past paper, you will get those questions. So try to solve question paper up to 2010, from 2021 to 2010, solving a question related to nuclear physics chapter. Okay, now go through the question properly. The power for a space probe, to be supplied by the energy released when plutonium-236 decays by the emission of alpha particle. Now, what is a space probe? You can see two space probes. The first one is called Voyager 1, and the second one is called Cassini-Huygens. The first one is sent to different location of space, like nearer to Jupiter, Saturn, to study about different location of space and also different planet. And also Cassini-Huygens, it's sent to one of the moon of Saturn, which is called Titan, for different exploration. We are not going to go into that. So I'm just showing you this diagram so that you can understand what a space probe look like. Though you don't need to know about space probe, what is a space probe or what's the use of space probe. You don't need to know about that for answering this question. I'm just showing it to you so that you can have a little bit of idea. Okay. Now, the power for a space probe is to be supplied by energy released when plutonium-236 decays by the emission of an alpha particle. Now, why do we need to use a radioactive particle for powering a space probe? Now, this space probe, they're going for a journey of very long distance, like Saturn, Jupiter. They're millions of miles away from Earth. So it's a long distance journey. So when the engineer and the people related to making of this complicated, complex machine, they need to think about the mass and the volume of the machine. I mean, it needs to be as small as possible. So one of the components, the power supplying device, that also needs to be very comparatively smaller, or as smaller as it can be. So that's why they're using this radioactive theories, radioactive knowledge related to radioactivity for powering the device, because a very small amount of radioactive substance can produce a quite good amount of energy. So that's why the size of the device that's going to power the space probe will be comparatively smaller. Okay, and this Voyager 1, it took 3 years to reach close to Saturn, and this space probe, which is called Cassini-Huygens, it took 7 years to reach to Titan, one of the moon of planet Saturn. But it took a different route. That's why it has taken comparatively more time, and also its mass is quite heavier. Anyway, so that means it's a long journey, and for long journey you need to give enough fuel, and if that fuel is radioactive particles, radioactive substances, so with a very small amount of radioactive substance, it can power the space probe for a very longer period of time. Now, so look at the question again. Power for a space probe is to be supplied by the energy released when plutonium-236 decays by the emission of alpha particle. So that means plutonium-236, a radioactive particle that is emitting alpha particle, and the associated energy of alpha particle is converted to electrical energy, which is powering the probe. The alpha particles, each of energy 5.75 mega electron volt, are captured, and their energy is converted into electrical energy with an efficiency of 24%. So that means this alpha particle will have kinetic energy mostly, and those energies captured, and they're converted to electrical energy with certain amount, with a certain quantity of efficiency, which is 24%. So the first question, we need to calculate the energy in joules equal to 5.75 mega electron volt. Now, electron volt, you already know that it's an unit of energy. Like when we deal with very small amount of energy, we generally convert it into electron volt so that we can have a better value. Better value means something like at the order of. Okay, so look at the first question. Calculate the energy in joules equal to 5.75 mega electron volt. We already know that unit of energy is joule, and electron volt, it also an unit of energy. Okay, when we are dealing with very small amount of energy, like energy of a photon particle of any electromagnetic wave, or kinetic energy of a moving subatomic particle like neutron, okay, or energy of a moving electron. So those energies are very small, and so for easy use of those values, we need to convert it into electron volt, which will be comparatively easier for us to use. And you also know about mega electron volt. This mega, this is actually a prefix. You have studied these prefixes in your AS level, like mega, giga, peta, milli, nano, centi. You have learned about those on AS level. So we need to convert this mega electron volt in joule. So it's very easy, and it's not strictly related to this question. So if we want to convert it into joule, at first we will convert from mega electron volt to electron volt. So we need to multiply it with 10 to the power 6, or 1 million. 1 mega equals to 1 million. 1 megawatt equals to 1 million watt. 1 megajoule means 1 million joule. Okay, 1 megapascal means 1 million pascal. So from mega electron volt, if you want to have electron volt, we need to multiply it with 1 million. Then we need to convert it into joule. Now 1 electron volt equals to 1.6 into 10 to the power minus 19 joule. 1 electron volt equals to 1.6 into 10 to the power minus 19 joule. Memorize it. So the whole mega electron volt is now converted to joule, and the value will be, the value is already calculated, 9.2 into 10 to the power minus 13 joule. So that's the answer. Okay, you will get 1 mark for that. Okay. So we are done with this question. So let's move on to the second question. The second question. In second question, we need to find out the number of alpha particles per second required to generate 1.9 kilowatt of electrical power. So 1.9 kilowatt of electrical power means 1.9 kilojoules of energy per second. So that's a lot of energy, 1.9 kilojoules. So definitely we are going to need a good number of alpha particles, because one alpha particle is producing 5.75 mega electron volt, which is 9.2 into 10 to the power minus 13 joules of energy, which is a very, very small value. Okay. Now, how we can solve this question? So let's consider we're going to need n number of alpha particle within t time. So that means n number of alpha particle per second. Now, each of the alpha particle is producing or having an energy of 9.2 into 10 to the power minus 13 joule. So n number of alpha particle will altogether produce 9.2 into 10 to the power minus 13 joule. Now, all of this energy of alpha particle cannot be converted to electrical energy. Why? Because in the question it is given that, in the question it's already given, the alpha particles each of energy 5.75 mega electron volt are captured, and their energy is converted into electrical energy with an efficiency of 24%. So that means 76% of the alpha particles energy is going to be lost to different form, and we will be able to capture 24% to electrical energy. So this alpha particle energy is needed to multiply with 24%, because we will be able to convert only 24% of this energy into that energy, I mean 1.9 kilojoule per second. Now 1.9 kilowatts, so that means 1.9 kilojoule per second, kilowatt or kilojoule per second. Let's convert it into watt, because we need to keep it in SI unit. So 1000 watt. Okay, maybe some of you are confused that in the right side this is watt and the left side this is energy. So it's not correct. Left side it's also watt. How? Because this is energy and this is energy, and T is time. So energy divided by time is power. So right side we are dealing with power, left side we are dealing with also power. And we need to find out number of alpha particles per second. So that means we need to find out n by t. We need to find out n by t. Now you just need to do the calculation, nothing else. So n by t into 24%, so 9.2 into 10 to the power minus 13. 24% means 24 divided by 100. When you remove the percentage sign, you need to divide it by 100. Now just make n by t as the subject. This is simple mathematics. If you calculate it, the answer will be 7.85 into 10 to the power minus 9. So that means per second we are getting this number of alpha particles. Per second we are getting 7.85 into 10 to the power minus 9 alpha particle, which will be enough to produce 1.9 kilowatt of power. So 7.85 into 10 to the power minus 9 per second. That means in 1 second, this number of alpha particle needs to be produced for producing a power of 1.9 kilowatt. Okay, I think you have understood. So let's move on to next question. If plutonium-236 nucleus on disintegration produces 1 alpha particle. This is a very important information. Okay, very important information. Each plutonium-236 nucleus on disintegration produces 1 alpha particle. Plutonium-236 has a half-life of 2.8 years. Calculate the decay constant of plutonium-236. So when you are having half-life and when you need to find out decay constant, so you need to know the formula which relates between half-life and decay constant, which is half-life equals to ln 2 divided by lambda. Lambda is the decay constant. So half-life is 2.8 years. Look at here, half-life is given in year. The time duration is given in year, but lambda needs to be, or decay constant needs to be found out in second. So that's why 2.8 years, it has to be converted to second. So lambda equals to ln 2 divided by 2.8 into 365 days into 24 hours equals to 3600 second. Because 1 year equals to 365 days, 1 day is equals to 24 hours, 1 hour equals to 3600 seconds. So if you calculate it, the value of lambda or a decay constant will be 7.85 into 10 to the power minus 9. 7.85 into 10 to the power minus 9 per second. Okay, so what was decay constant? Decay constant is the probability of decaying of a nucleus. Like say, for example, I'm giving you 10 plutonium-236 nucleus, and you have picked one of the plutonium nucleus, and the probability of that particular nucleus will be, probability of decaying of that particular nucleus will be 7.85 into 10 to the power minus 9 per second, which is a very less value, and it's supposed to be less value. Why it's supposed to be less value, I have discussed it in my class lecture elaborately. Okay, fine. So let's move on to next question. Now, let me remove this two figure. We don't need it now. Now, use your answer in A2. Use your answer in A2 and BI to determine the mass of plutonium-236 required for the generation of 1.9 kilowatt of electrical power. Now, this is very related. We need to use the answer of in A2. Now, what do we have? What we have got from A2? From A2, we have got in 1 second how many alpha particle is needed. So from A2, we have got how many alpha particle is needed for producing 1.9 kilowatt of power. And B1, what did we find? What did we find in B1? That the decay constant, which is 7.85 into 10 to the power minus 9. So in this question, we need, by using A2 answer, that means number of alpha particle needed to produce 1.9 kilowatt of power, and BI, where we have calculated the decay constant value, and we need to use this two data to determine the mass of plutonium-236 required for the generation of 1.9 kilowatt of electrical power. Now, how we are going to do it? So at first, we need to find out activity. What was activity? Activity is the number of nuclei decaying per second. Activity is the total number of nuclei decaying per second. Now, what is the decay constant? The decay constant was 7.85 into 10 to the power minus 9. And what was activity? Activity was the number of nuclei decaying per second. Now, there is a crucial information that was given in question B, which you need to understand, which you need to know actually. Each plutonium-236 nucleus on disintegration produces 1 alpha particle. And we were requiring 7.85 into 10 to the power minus 9 alpha particle for producing 1.9 kilowatt of power. So that means if you want to have 7.85 into 10 to the power minus 9 alpha particle, you're going to need this number of plutonium that should decay, because this number of plutonium nucleus, if it doesn't decay, then we are not going to get this number of alpha particle. So number of nuclei, number of plutonium that should decay is equivalent to the number of alpha particle. That means 7.85 into 10 to the power minus 9. And this n, what this n is representing? This n is representing the total number of nuclei that we should have if we want to decay this number of plutonium. Like, say for example, right now you are having 100 plutonium atom. Are all the atoms are going to decay in the next second? Definitely not. According to activities, some of them are going to decay. Maybe 10 out of 100 or 500 out of 100 or 10 out of 100 will decay in next few seconds. So similarly, we need this number of plutonium nuclei, that should be decayed. Otherwise, we are not going to get this alpha particle. But if we want to have this number of decaying plutonium nuclei, then original number of plutonium nuclei has to be greater, which is n. From here, we will find out the value of n. The value of n is 1.096 into 10 to the power 24. Okay, fine. So we have got the total number of plutonium nuclei that should be there if we want to produce 1.9 kilowatt of electrical power, but we need to find out the mass. Now, if you have proper knowledge from ideal gas or mole from chemistry, so you know that from this value we can find out the mole, the equivalent mole of plutonium. So what should be the mole? Mole equals to number of available atom nuclei divided by Avogadro number 6.023 into 10 to the power 23. If we divide certain number of nuclei or atom by Avogadro number, we will have the mole here. And if we want to find out the mass, we need to multiply this mole. We need to multiply this mole by the atomic mass of plutonium, which is 236. So the answer will be in gram. The answer we are going to get here will be in grams. That's 430 gram. Okay, 1 second. Let me calculate it again. So actually 429.44 if you round it off. I mean, if you write down in two significant figure, it will be 430. So 430 gram of plutonium is needed if you want to produce 1.9 kilowatt of electrical power. Now, 1.9 kilowatt of electrical power, it's not that less, but you are going to need only 430 gram. So that's why for running space probe, they are using radioactive nuclei, because with a very small amount of radioactive nuclei, you can produce good amount of power and you can power the space probe for a longer period of time. Okay. Anyway, so let's move on to next question. The minimum electrical power required for the space probe is 0.84 kilowatt. Now, this is a very important question. The minimum electrical power required for the space probe is 0.84 kilowatt. Calculate the time in years for which the sample of plutonium will provide sufficient amount of power. Now, before explaining this question, I need to explain something from the book. Okay, I'm going to explain something from the book, which is very necessary to understand it. And if you face this type of question, then you will be able to answer all of them if you can understand the content that I'm going to show you from the book. Okay, so I will listen carefully. So, I'm following this book. You can also follow this book. It's a very good book, and it's written based on a new specification. The exam for this new specification is going to be started from May-June session 2021. 2022. Okay, now this is the nuclear physics chapter, page 377. Now look at this equation. Here, n equals to n naught. N naught, this 0 stands for NOUGHT. It means 0. Okay. And when we write something like N naught or P naught or A naught, we are representing the initial value of this particular physical quantity. Okay, like say for example, initial power, initial number of something, initial activity of a certain radioactive isotopes. So N naught, A naught, P naught means initial of something, initial quantity of something. Okay. So anyway, so this equation is representing, let's say for example, you are having 100 radioactive nuclei. 100 radioactive nuclei. So some of the nuclei is going to disintegrate every second or every minute. So the number is going to be reduced. So for example, after time t, the number is reduced to 50. Now, if I ask you what is the time duration, I mean, what is the value of t for which the number is going to be reduced from 100 to 50? So how you are going to solve the math? So initially you were having 100 atoms. So at the position of N naught, you will put 100. And N is the number of nuclei remaining after time t. N is the number of nuclei remaining after time t. So you will put 50 here. And from here, mathematically, you can find out the value of t, provided that you know about the value of the lambda. You know the value of the decay constant. If you know the value of the decay constant, then mathematically, you will be able to find out the value of t. And you can also write it in this form any way you like. Now, this is actually in case of finding out certain number of nuclei remaining after certain time t, you can use that equation. The same equation, I mean, same format of the equation can also be used to find out the amount of activity, the value of activity after certain time t. The formula will be like this. I mean, same formula, just you are going to change the N and N naught by A and A naught respectively. A naught is representing initial activity and A is representing activity after time t. Now, this radioactive particle, as radioactive decaying is going on, so definitely in every decay, it's going to produce some amount of energy in form of gamma radiation and heat. Okay, so say for example, right now, a particular sample is emitting 100 joules of energy, and after certain time t, now the sample is emitting, say for example, 30 joules of energy. Now, what is the time duration? You can use the formula. You can use the same pattern of the formula. Like say, for example, E equals to E naught E minus lambda. E naught is the initial amount of energy emitted by the sample, and E is the amount of energy emitted by the sample after time t. Now, if you want to find out the power, what is the power producing by the sample after time t? You can write the equation like that. P equals to P naught E minus lambda t. So that's why they have given a generalized equation, x equals to x naught e to the power minus lambda t. At the position of x and x naught, you can put n and n naught if you are dealing with number of nuclei. At the position of x and x naught, you can put a and a naught if you are dealing with activity. At the position of x and x naught, you can put E and E naught in case of energy calculation, or P naught in case of power calculation. So I think you have understood it. And this theory we're going to apply for solving the last question. Okay. The minimum electrical power required for the space probe is 0.84 kilowatt. Calculate the time in years for which the sample of plutonium-236, plutonium-236 in B2 will provide sufficient power. Okay. Now, initially we have calculated, it was producing 1.9 kilowatt of power. Okay. 1.9 kilowatt of power. And the question is, the minimum electrical power required for the space probe is 0.84 kilowatt. And as we are using radioactive particle as a source of electrical power, so over the time, definitely it's going to produce less and less amount of power. So we need to find out the time duration upon which the 1.9 kilowatt power will reduce to 0.84 kilowatt power. Okay, because if the power reduces below than 0.84 kilowatt, then the space probe won't run. So how do we calculate it? So we are going to use the general formula. The general formula was x equals to x naught e to the power minus lambda t. And as we're dealing with power, we can write down P equals to P naught e to the power minus lambda t. And you have to write like this. It's not necessary, okay, because you can directly put the values at the position of an x naught, x and x naught, no problem at all. Okay, so after time t, the power will be 0.84 kilowatt. We can keep it in kilowatt form, no need to convert it into watt, because in both sides the unit is in kilowatt. At P naught, 1.9 kilowatt, because initially we were producing, the sample was producing 1.9 kilowatt power. And e to the power minus lambda t, we knew the value of the decay constant. The value of the decay constant was 7.85 into 10 to the power minus 9. 7.85 into 10 to the power minus 9. And from here, we need to find out t. Okay, one thing, let's not write down the value right now of value of lambda, because we need to simplify the equation and we need to make t as the subject. So 0.84 by 1.9. We need to use the formula of ln to solve the equation. We will take ln on both sides. And this type of maths you are going to solve in P3, Pure Mathematics 3, in logarithm chapter. So minus lambda t, it will come at front. And value of ln e, it's 1, you know about it, or you will know in P3. So t will be minus 1 by lambda ln 0.84, 1.9. The value of lambda is 7.85 into 10 to the power minus 9. Sorry for my bad handwriting. Anyway, so here it's negative, doesn't matter, because this value is going to be negative as well. The value is ln it's also negative. So if you calculate it in calculator, the answer will be, it will come in second. Then definitely you need to convert it into, okay, let me do it. Okay, let me do it. So I'm getting 103975448.8 seconds. You need to convert it into year. If you want to convert the seconds into year, you need to divide by 365, because 1 year equals to 365 days. 1 day is equal to 24 hours. 1 hour equals to 3600 seconds. Then it will be converted to year. The final answer will be 3.3, approximately 3.3 years. So that means this radioactive source, it can power the probe up to 3.3 years. It can power the probe up to 3.3 years. After that, the power produced by the radioactive sample will be less than 0.84 kilowatt, which is not sufficient enough for this particular probe. Okay. So I think you have understood. And in comment section, if you have any problem in any physics or maths O-level, A-level related problem, or any question, write in the comment section, or you can also mail me in my mail address. and I'll try to respond. I'll reply, or otherwise I'll make a video and upload it. Thank you very much. Allah